Ya, Assalamualaikum warahmatullahi wabarakatuh. My name is Abdul bin Yaakob.
My name is Muhammad ZAMRI. So for this assignment, RF thermal microwave, we have a task for design a lab element filter, which is low pass filter and band pass filter frequency, and then we need to design the distribute signal. So Abdul will explain about the lab element filter.
Okay, for the lump element filter, there's two type of filter. That is a pi filter and T filter. So for the our project, I will use pi filter. Okay, next. Next is this is the 0.5 dB ripples low pass filter, and our this is the theory of the 0.5. And then the next one is figure 2. This is element value based on what we get from the 0.5 normalized auto attenuation vs normalized. And then next, this is a band pass filter. So for the first one, figure 3, band pass filter response, and then figure 4 is band pass filter schematic. All right. Next, this is a distributed element filter. So for this one is mostly use very high frequency, which is band 30 to 300 megahertz. At the figure 5, go to figure 5, and then this is a step impedance low filter. So as we can see here, actually we will get the answer from layout like this. And then okay, let's we go to realization design. Okay, for the low pass filter, the cutoff frequency is from my project is 2.9 gigahertz, and then the insertion loss is 35 dB, and followed with 7.2 gigahertz, and then the ripple is 0.5 dB equal ripple. So we need to calculate the omega, which is 2 pi f. We get 45.24 gigahertz, and then omega fc, omega c, which is 2 pi fc. We get the answer is 18.22 gigahertz, and then for the calculation, and we get to find the ripples based on uh, go down one. Based on the table, we got the value of n by using this 1.5, which is at the bottom one is 1.5 at the red line, and then for the dB is 35. So the ripples, the n that we get is n4. So the next one, so because of n equal to 4, so I will use the value of 4, which is G1 1.6703, and then G2 1.1926. For G3 is 2.3661, and then G4 is 0.8419. So I will use until G4, and then after we get the G1, we need to calculate the capacitor and inductor. So by using this formula, G1 divided by RO with impedance, followed by omega C. So for the C1, we get the answer is 1.833 picofarad, followed by C3, which I will get 2.597 picofarad. And then for the inductance, which is L2, I get the answer is 3.272 nanohenry. And then L4 is, I get the answer is 2.446 nanohenry. Okay, let's go to the next one. So for the schematic that I have do, which is a schematic of the LAM low pass filter. So at the here, we first one is capacitor, followed by inductor. This is a pi filter that I will use, and then I will get the answer output for this schematic is for the M1. M1 is 7.2 gigahertz that I mark for the question that I have given. And then for the M2 is 2.9 gigahertz, which is dB 1.804, 1.840. Okay, next. For the distributed design, what we get for firstly, we need to know the G1. The G1 that G1 until G4 that I used the 0.5 table. So for this one, for Richard transformation, basically for this one, what I got the value 1.1926 is the inductance. Inductance that I need to calculate by using transformation. So for the capacitor is actually I'm not for the capacitor. For the capacitor, I will calculate. For the inductance that I will not calculate. So based on this Richard transformation that I calculate is capacitor, and then the inductance I will remain the same one. Okay, next. This is a Kuroda identity implement. So at the first one, we need to identity the implement. Identity. So for the first one is Z1, assume as 1. For the Z2, use the value of capacitor, and 2 and square. I get the answer is 1.5986, and Z1 divided by n square 0.6257, followed by Z2 divided by n square. I will get 0.3744. Okay. For the normalizing, next one. Okay, for normalizing using Kuroda implementation, so we need to divide it by 3 parts to calculate. So for the first part, Z1 is 0.3744 that we have calculated with the Kuroda identity implement, the first one. We need to calculate. For this step is the difference is n square is multiplied by Z1, followed by n square multiplied by Z2. For the first line, I get the answer from here, and then followed by part 2, which is the same concept, same calculation, and the last one is calculation with the last part of my project. So after we normalize the impedance, we normalize the Kuroda implementation. Next, we go to normalize impedance for different stub. Okay, from a different stub, actually what we get from the Kuroda implementation, the value what we get from in there, we need to put at here, which is the value we get 3.6740 is from part 1, just now I explained. And then followed by the value that we get, and then after we normalize the impedance from a different stub, and then we go to denormalize with 50 ohm impedance for different stub, which is the value we get from normalize is multiplied by 50 ohm. So
I can hear you.
one.
Okay, I can hear you.
Okay, for the next one is 1.3744 is multiplied by 50, and then we get 68.72. Okay, next one. Okay, next, this is a schematic before turning, which from the demolize with 50 impedance, and then we get the output. We get the output from this schematic is here with 7.2 gigahertz and 2.9 gigahertz, and then from here is some distort, and then after tuning this turning parameter, and then we need to schematic. This is a schematic turning with from the impedance. And then lastly, I will get the output after turning is this one. It's look like a low pass filter. So right here 7.2 gigahertz, and here is 2.9 gigahertz. And then lastly, for the low pass is design layout for distributed LP design. So for the schematic, this is my schematic layout. So the next one for the band pass, I will pass to Muhammad Afwan. Afwan.
Yeah, thank you, my friend Amrul. So here for the band pass filter, the value given is we need to find the F1. The bandwidth is 300 megahertz. So here the center frequency, the given center frequency is 2.9 gigahertz. For find the F1, the center frequency 2.9 gigahertz. Subtract 300 megahertz divided by 2, and I get the 2.75 gigahertz. For the F2, 2.9 gigahertz multiply pass by 300 megahertz divided by 2 and get the 3.05 gigahertz. So next we find the omega 1. The omega 1 is 2 pi f1. So the value of the f1 multiplied by 2 pi, and get the 17.28 gigahertz. Next, omega 2, 2 pi f2, the value of f2 multiplied by 2 pi, and we get 90.16 gigahertz. Next, for the omega naught, 2 pi f naught, so The value of F0 is 2.9 gigahertz, multiplied by 2 pi and get the 80.22 gigahertz. Next, we find the delta. Here for the formula, and then the delta value is 0.1. So the n value I have already given is 5. So and this system is 3 dB equal ripple. So here refer to for table for 3 dB ripple, and for n5 here the value for the G, but I will take only until G5. So here the value for G1 until G5 3.4817, 0.7618, and so on. Okay, so here are the calculation for the capacitance and inductance. So for the shunt capacitance and inductance, here are the formula for inductance. Delta R naught divided by G1 omega naught. Here the calculation and here the result for the shunt. We have L1 and C1, L3 and C3, L5 and C5. For the series, we have L2, C2, L4 and C4 for the series. So here are the calculation for the L2 for series. Here are the formula, and here are the formula for the capacitance, and here are the value for the L2, 20.906 nano Henry. Yes, C2 is 0.144 picofarad, so and so on. Okay, here are the schematic of bandpass filter. Here are the shunt capacitor inductance, and these are the series capacitor inductance. We design the ADS. After that, we find the output. So here are the output for the bandpass. Here are the graph for bandpass filter. And for the M1, we put the F1 2.75. For M3, we put the F2 3.05 gigahertz. For M2, we put the center frequency, which is 2.9 gigahertz. So that's all for the result. And so we have already doing the task by using for the low pass using the 0.5 dB ripple. So we refer to the 0.5 dB ripple graph and table ripple element value for the low pass filter, and we get the number of order is 4. So we use a value of G1 to G4 for the low pass. And next we design the distribute design. Then we use the Kuroda identity to convert the shunt stub into series stub. And next we design the bandpass filter by the given value, which is 2.9 gigahertz, bandwidth 300 megahertz, and is a 3 dB equal ripple. As conclusion, all the tasks have already simulate and analysis using ADS, and we get the output. So all the simulation already show in this report. So that's all from me, Muhammad ZAMRI, Muhammad AFWAN, and Abdul Rauf for this video. Thank you for watching.
Thank you. Thank you very much.
Assalamualaikum warahmatullahi wabarakatuh.